Skeletal muscle, fairly large mass of tissue, and does not require a great deal of blood at rest, but when you need more of it, you need to be able to get it quick. Okay? So what you have are neural controls, and they do participate in reflexes. Okay? And so when your sympathetic nervous system increases its activity, you get vasoconstriction in the muscle, and you will get an increase in blood pressure. Okay? It requires a large increase in perfusion with increased tissue activity, contraction, and it gets that. Okay? And there is local recruitment of capillaries. And what you have are these metarterioles that go between the arteries and the veins, and you have these precapillary sphincters everywhere. And what happens is you dilate those sphincters and you open up capillaries that aren't usually open when there's a high oxygen demand. And so you get capillary recruitment. So this makes no sense to anyone anywhere. The fact that you reduce circulation to the skeletal muscle capillary beds when you increase sympathetic activity, because we all know that when you increase sympathetic activity, often that's because you're exercising and you need to run away and your muscle needs more oxygen. So here's how it works. Okay, my right arm is exercising. Okay, for guys like me, this is what passes as exercise. Okay. My left arm, worthless and weak. Okay, not moving at all, lazy. Okay. Now, if I'm the body, I want to increase flow to my right arm because it's doing the work. And my left arm has not earned any blood. Okay, it's, you know, it has no business getting extra blood. You want to cut blood off to my left arm because it hasn't earned it. Okay, bad arm. Now, what's happening in my right arm, even though there's almost no load on this muscle, is it's getting tired. Metabolites have built. This is what happens when you're out of shape. And I'm getting dilation of the arteries in this arm because I'm building up metabolites. And because my sympathetic nervous system is high, because even though I'm not really doing much exercise, just doing anything causes my anxiety to go up, and my sympathetic nervous system kicks in. And I'm getting vasoconstriction in my left arm because I don't need extra blood flow in my left arm. So the body has designed the system such that only the muscles that need the blood flow get it. And the other ones participate in maintaining mean arterial pressure. Okay? I'm exercising, I'm dilating in my right arm, my total peripheral resistance has fallen, my mean arterial pressure wants to fall, my body is doing something about that to maintain it, and what's happened is the sympathetic activity has gone up, and I'm constricting in my left arm in an effort to maintain blood pressure. Okay? So that's how the interaction works, and that's why it kind of makes sense. The local controls override the sympathetic response in skeletal muscle. Increased demand, increased flow, but only where you need it. Constriction everywhere else to maintain blood pressure. Okay? All right. I've already run over by 3 minutes. I feel terrible about that. We'll pick this up in about 7 or 8 minutes, and we'll take a break. Okay. So we were going through our skeletal muscle here, and we talked about all this and the exercise, and now I want to talk a little bit about the muscle pump, also related to exercise. So this is a way that you can maintain venous return during exercise, okay? And it's got to do with the action of your skeletal muscle contracting and squeezing on the veins. As you guys know by now, the venous walls are more compliant than the arterial walls, and they squeeze together pretty easily. And the veins actually have one-way valves in them, similar to your heart. They're not as efficient, but they allow flow to go one way, and they only allow flow reasonably, within reasonable limits, to go toward your heart, okay? So here we have a dude, maybe a woman, who knows, somebody, quietly standing, and the veins are open, and blood is flowing from the foot back up toward the heart, okay, through our valves. Now, we take a step and we compress that section of the vein and we increase the pressure. Now up here, the pressure behind the valve has exceeded the pressure in front of the valve, and we eject blood toward the heart. Okay? Down here, because the pressure went up and the pressure in front of the valve exceeds the pressure behind the valve, this valve closes. And so blood flow isn't really allowed as much in this direction because of the existence of this valve. Instead, it's forced toward the heart. And you get more filling in the heart when you're contracting your muscles and you're exercising. And now we finish our step, our muscles relax, our veins open up, and now what happens is the pressure here decreases. And now the pressure in front of this valve exceeds the pressure behind this valve because you've let off, but the valve's empty, but the vein's empty, the pressure's low. And so what happens is this valve closes now because it doesn't want to allow flow back into this area, and instead this valve opens. The pressure is now low here and higher here than here. This valve opens and blood flows into that area as relaxation takes place. Okay? And then the whole process starts all over again where you compress and force it toward the heart. So that's called the muscle pump, and it increases filling, it increases venous return during exercise. Okay? Last thing I want to talk about is the brain. Of course, it is within a rigid container, and that means that any increase in volume in the cranium is going to cause a fairly big problem with the vessels because it's going to compress the vessels. You can only get so much volume within your skull, and then you start to limit flow. So similar to the heart, it has to receive oxygen, and it does. They don't obviously participate in maintaining mean arterial pressure. You're basically maintaining mean arterial pressure to keep the oxygen flowing to the brain. You don't want to vasoconstrict the vein. So they really don't participate in sympathetic responses. And instead, there are very strong metabolic controls, okay? Increased carbon dioxide acts as a very potent vasodilator in your brain. And the control is really exquisite. So this is a figure out of your textbook. And you'll notice that if you measure flow to different regions of the brain with like a catheter or something, okay? And what you get at rest is this. You get certain regions that are more perfused than others. But as soon as you start to move your hand, now the blood flow is maximal in different regions, and it's maximal in regions that are associated with causing your hand to contract. And you can literally measure the increase in flow to the different regions depending upon what regions you're using. That's how little increase in metabolism that you need. If I clench the hand, instead of just stimulating it a little bit, I get this. If I'm reasoning, I get this blood flow. And if I'm reading, I get blood flow to different areas, presumably involved in vision, things like that. Okay? So literally different local areas of your brain get different flows depending upon what you're doing with it. Okay? The control is really exquisite, and you get hot spots. Okay.